All right, so this video is going to be about the chapter 4, basically the lecture, or at least most of the lecture. So let's get started. All right, first thing you need to know. What we're talking about here is the surrounding context of a network has an effect on the structure of the network. The main topic in this chapter is what's called homophily. Homophily is the tendency for like things to stay together or stick together or associate together. In a social networking setting, homophily means that nodes will generally have edges to other nodes that share similar characteristics. This diagram I'm showing on this slide is the one about this, I believe, is male and female, and we're showing here that the male gendered people in this network tend to associate together, and the female gendered nodes tend to associate together, while there's not especially a lot of cross-gender edges. So what is the surrounding context? The first thing we need to define here is what a contextual characteristic is. And so any characteristic that is outside of the network graph that is going to influence or is influenced by edge formation is part of the network's surrounding context. We have generally two, I guess we call it pressures, and they go into and out of the network. The first pressure is selection. That's directly related to this homophily idea and associating with things that are similar to you or nodes similar to each other. So in a selection situation, if we have nodes that are similar to each other, we expect more edges to form between those two nodes. The other end of it, so the pressure coming from the network out, is social influence. And that is, as nodes associate with each other, they will tend to develop similar characteristics. Talk about some issues this raises later. You can see in this network we're talking about people, what do we got? Bob, Anna, Claire, and Daniel, and there's membership in a karate club, and Anna does literacy as a volunteer, and we can see here that people are associating with each other. So now we'll talk about homophily. Homophily is very exciting. So we can actually test this. So this is our figure here. This is actually from page 188, or page 88 in the text, and they actually go through this, but I'm going to go through it again, and I will talk about what you really need to know, I guess. So in this sample, remember what we've done as a researcher is we have sampled some aspect of the population. In this sample, 1/3 of the nodes are female and 2/3 of the nodes are male. Therefore, in this sample of the population, so whatever we're modeling here, and remember we are the ones who defined the edges. What does an edge mean? This might be people emailing each other. It could be people that are Facebook friends. So someone defined that. They took a sample. Now, if we got 1/3 female and 2/3 male, if we associated them randomly, you would expect 1 out of 9 of the edges would be female to female. That is, it's because it's 1/3 of them are female, and you multiply 1/3 by 1/3. That means the edges between them are going to be 1/9. 4/9 of the edges are going to be male to male. That is, 2/3 of them are male. If all the male things connect to each other, you're going to end up with a proportion of 4/9 of the population, or the edges would be male to male. And then the female to male edges, remember 1/3 are female, 2/3 are male. So if we take 1/3 times 2/3, And then you have to basically do the reverse, 2/3 times 1/3. That's why it's 2 times 1/3 times 2/3. So 4 out of 9 of the edges should be female to male. And if you added up all the possible edges, is there really 9 here? Remember, we could do our 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. That would give us all our possible edges, and actually we don't have to do that. So once we've determined that, we can now measure and actually say, does this network exhibit significant homophily? So we measure this and we look at the actual female to male edges. So we look at the ones between what color is that? The salmon and the white. And we find there are actually 5 edges out of the 18 edges in proportion that are female to male. And then you use a statistical test. You might know this from, hopefully you remember this from your statistics class, the population proportion. And what you would find actually in this situation is we have a set here. There's, if we're thinking about the edges, there's only 18 edges in our sample. So a sample size of 18 edges, and we have 5 out of 18 are expected to be female, or are female to male. We would expect over there it's 4 out of 9, which would be 8 out of 18. If we did a statistical difference there, you would actually find it's not significant, and it's because your sample size is too low. For this test here, if the proportion is 4/9 versus 5/18, I think you need about a 50 or 60 sample size in terms of edges. But so it's statistics. So remember that when you're doing tests, don't forget there are statistics here. In the book, they're like, hey, this looks like there is homophily, and sure, it looks like there is, and that would be the kind of thing like a researcher would say, yeah, the means are higher, but you can actually test this statistically, so you need to do it. So, test of homophily, very exciting. All right, affiliation graphs. So we talked about external characteristics from the graph. And so let's say we have a graph that has a bunch of, in this case, this is board members. And we're wondering how are the board members sort of linked together. The affiliation in this situation is our normal node is the board members. The affiliation is the company they're actually the board of. So on the left, we're graphing here the nodes, and the right is their affiliation. So some people would argue that they are both nodes, the affiliation and the actors. I would tend to argue no, because we define a node as having agency. Either way, you can graph them this way. This is what's known as a bipartite graph, and we've just linked all of the people, nodes on the left, and their affiliations on the right. And we are kind of looking at what they have in common. So if we look at this, we can hopefully see, for example, we've got Al Gore, Arthur Levinson, Steve Jobs, and Andrea Young that's on the Apple board. And so you would expect that there would be edges between them. Notice on here, we don't draw those edges, so nothing between Al Gore and Steve Jobs. I don't know, we aren't measuring whether they sent emails to each other. I don't know. But we aren't showing that because we just didn't. And if we don't show those links, then it still remains what's called a bipartite graph, meaning all the things on the left are only linked to things on the right. All the things on the right only linked to things on the left. None of the things on the left are linked together. None of the things on the right are linked together. So here's why did we even bring up affiliation? Well, the social graph and the affiliation graph tend to evolve together. We talked a lot last chapter about triadic closure, where if two nodes have edges with another node, they tend to form an edge between each other. So they have a higher probability of forming an edge between each other. Now we're going to talk about 2 more forms of closure, focal and membership closure. The definitions are listed right here, but there's a little more detail I want to go through, so we'll handle them each one at a time. So again, we've done triadic closure. Two nodes have edges with another node, and they form an edge between each other. Remember, the idea here was we're trying to describe, here's the network at time 1 with A and B connected, with A and C connected, and we're trying to say at time 2, we expect with some probability that B and C will also have an edge between each other. That was last chapter. Now we're more interested in networks and their surrounding context, right? So we are interested now in, for example, sort of more about the why B and C form links to each other. And the funny thing is we aren't actually going to talk about that, but here we go. All right, next form of closure was called focal closure. Focal closure is about those affiliations. So here we have nodes of B and C, and we have an affiliation or a focus, which is focus A. So we're going to say here, if two nodes have edges with the same focus, we expect at time 2 that those two nodes will form an edge between each other. Remember, if we think back to the Apple board, eventually you would expect, Al Gore and Steve Jobs to have sent an email to each other or something like that. Membership closure also involves these affiliations. What we're talking about here is where if we have two nodes in a network that have edges with each other, one of the nodes has an edge to the focus, then we would expect the other node to have a certain probability of forming an edge to the same focus. So remember, this is networks and their surrounding contexts. Our link here is between A and B. Yes, we do graph C, and there might be, it's a different edge there, right? So if we're thinking back about like the karate club example, this is, A is a member of the karate club, A and B are good friends. Eventually, with some probability, we would expect B to also join the karate club. All right, so there's been a fair amount of research on these, and sort of to determine, given those closure effects, like what is the tension in the network and how strong is it? The first one I'm going to show you is that email study of college students. And what they find with this one was, if you look at, people who have sent emails. So if I'm person A and I've sent an email to person B and I've sent an email to person C, what's the probability that persons B and C are later going to send an email to each other? So they did that over time, and then it was also based on the number of what they called common friends, right? So if I'm, for example, B, and I'm thinking about emailing C, well, if there's just A in common, then I would have one common friend. If there's a D out there that has me and them in common, etc., what is the probability then of it, of me actually sort of closing or making that edge? Looking at it over time, that's the graph you were shown, and that's this sort of hockey stick style graph where, just one friend, one common friend, it's still a fairly low probability of that edge forming. But as you hit 2, 3, 4, 5, and then especially, going on and up from 9, it really goes up a lot. So what they're saying here is it's sort of an increasing probability that a link will form, not linearly, but exponentially. There was the caution here that if you looked at the number of common friends being 10, that actually happened fairly rarely, because most of the time if someone had that many friends in common, they would have already sent the email. So those, that's sort of a rare event, but definitely proof of this exponential function. All right, so that's triadic closure. If you look at focal closure, the people with that email set also had the class enrollment. And they looked then at the probability of you sending an email to another person based on whether you had, or how many classes you had in common with them. and this is the graph they got. And what they found here is there's diminishing returns to that one. So with foci being the number of classes you have in common, once you get up to about 3, yes, those links are in a linear basis likely to close, but once you hit 4 or 5, those extra foci don't really increase the odds. So that was diminishing returns for that focal closure one. For membership closure, this one, there was actually a couple of these. One was in LiveJournal. I don't remember offhand what the other one was in the book. But this one was, what is the odds that you're going to join a community given the number of your friends that are in that community already. And you can also see here a diminishing returns. A lot of these do kind of make sense. That is, if you have 50 communities, you're not really going to be keeping track of them. Just the same as, at 5 classes, it just kind of gets to a diminishing level of return. So again, a common of friends that are in this community, number of friends, is what the probability that you're going to join. Even if there's 50 friends, starts out kind of linearly. And then you get diminishing returns. So this is just some of the research. It kind of went on and on. This one here I thought was interesting about the Wikipedia one. And here we're trying to get at the idea of selection versus influence. That is, to what extent do you join a group because it's the same as you, versus the extent to which you have this group membership or this link and you become similar because of that link. And so here's some researchers trying to sort of examine it. And what happens here is you have a sense that as you are editing the same Wikipedia articles, you maybe start to realize that you're seeing the same name all the time. That's the selection idea. So you have a common interest and you're like, oh, this person has a common interest to me. This time 0 in the graph is when they first actually send a message to each other, first message. After they've messaged each other, they're starting to call it social influence, and that is there is an amount of similarity that rises really quickly. That is, you keep editing or look through basically their list of articles maybe and edit those also. But then over time it sort of levels off and you might, whatever ones you were going to edit the same as them, you just might have kind of done it before. So this was, again, this is not really, well, it is kind of about closure, but it's, is there closure because of selection? And then once there is closure, how does that make you more or less similar? All right, just a couple of things that need to be emphasized out of chapter 4. I've alluded to some of these already. You may not have gotten them already out of the book, but here's some more important stuff. The first one is there is that whole segregation modeling, and I am, I would say, rather, I don't know what the good word for it is. I don't exactly like it. So if you look at these ideas of homophily, remember we have selection and influence, and that means if you observe segregation in a network, it could be because of selection. That is, what we were looking at it's kind of what they're looking at when they're doing the little red dots and blue dots. That is, people choose who they're going to associate with. But you got to remember too that the structure of a network is also about, I don't know if you'd call it influence, but there is a certain amount of control in some of these. And so they don't model in the red dot, blue dot model. That is, if we just said, okay, the red dots don't like living by blue dots, the blue dots don't care. And if you ran the model with just that, you would probably get the same result. My point here is, as a researcher, you need to make sure you're not stumbling over the cause and the effect in your modeling. So if you design a model and you're like, okay, we can model, between time 1 and time 2, that doesn't mean that your model is actually modeling the behavior of the people. So just make sure you're grounding your ideas in a reasonable behavioral theory, let's call it that. So even if we look at selection and influence, things like this Chicago in 1960, it's super segregated. It's not because the African Americans didn't want to live by the white people. It's because the white people were doing things to prevent African Americans from living in other places. So, you can't say that, this segregation thing in a way is almost an excuse. The model becomes an excuse for what was really racist behavior. So, be good. Next thing is the same idea, but sort of extended. And this is something I found in my own research. You remember we're talking about selection here, and we're saying, given certain characteristics, people are going to, congregate with the same people. We talked earlier about this one that was the male and female links, and that the females tended to form edges together and the males tended to form edges together. And as a researcher, when you do that, you always end up having to explain why. And so if I, as a researcher, found that there was this homophily in this network, I might start saying, the males are more aggressive and the females are more nurturing, and I might come up with a bunch of rationales of why it happened. The problem is the rationale for why it happened is actually the theory, and that's the theory I should be testing. Like, just because I found that males and females behave differently, it doesn't explain the behavioral choices that happened in the network. And so an immutable characteristic like that is almost, in a way, useless. And there's a lot of that too if you do it on personality tests and other things. And if you talk about people forming edges based on their personalities and they cluster together or they do with complementary things, personality is supposedly immutable, and you actually need to come up with a better explanation of why that's happening, rather than the basis of whatever the personality is. There's some driver there, and it's moving. I guess the next thing I want to say is a lot of times these what we call immutable characteristics, they're usually not super, in this case, dichotomous. If we say male and female, there's not any male, female, exactly one type of male and exactly one type of female. That's what I mean by they're not dichotomous. And it's also not a stepwise. There's not these hard and fast steps. There's a lot of continue out there, and you just don't want to do it. So that's kind of an uncomfortable thing, but be good about your research, and this is part of the things that'll run you into problems. All right, so that's it, and we'll continue on with other stuff.